So today I want to talk to you about this idea that materials matter, and that, looking to biology, we can find biologically inspired alternatives to conventional neural nets that can actually improve our ability to do meta learning in particular and accomplish our goals in AI in general. And so I just want to be clear that these are things that are loosely inspired by biology, but I'm excited to share them with you. But before I do that, I actually want to tell you about a little bit of work that I have a feeling this community will find interesting that normally I wouldn't dive into, but I think you might like it. And this is kind of into this question of the evolution of structural organization. So I've spent a huge part of my career looking into why biological networks like genetic regulatory networks, protein-protein interaction networks, and become modular and hierarchical. So modularity is the localization of function in an encapsulated unit. Like in a car, you've got the different pieces of the car. In your brain, you've got totally different areas of your brain. Same thing as software, et cetera. And it's long been believed that this modularity increases complexity and adaptability because you can recombine these building blocks in new ways. Interestingly, in the field of evolutionary computation, where we try to say evolve neural networks, we never ever see modularity show up. It's supposed to be such a good thing. It's in every brain, every animal brain. It's in our bodies. It's in software. Why doesn't it show up on its own? So we always got this entangled spaghetti code like you see on the left, and almost never got the stuff that you see on the right. So my colleague Jean-Baptiste Moret-Hadlipson and I looked into this question quite a while ago now, and I thought you might find it interesting. So we took a problem that is known to be modular. This is problem here. You can either solve it by solving it all at once, or you can first solve the left side and the right side and put them together, as you can see down here. And then we looked into this, basically we kind of looked into the neuroscience literature, and I found this hypothesis that was actually proposed by Ramon y Cajal, in 1890 something, 99. His basic hypothesis was maybe modularity doesn't show up because it's a good idea. Maybe it shows up because it's just expensive to have connections in your brain. You have to house them, you have to maintain them, and you have energy drop along them, et cetera. And so there's this great opportunity in silico to test things that you can't test in nature, which is to say to evolve networks with and without a cost for connections and see if that's the true driver. And we did just that in this paper. And basically what you see is that if you do reward normal RL or normal evolution just based on performance, you get these spaghetti code non-modular networks and they then are slow to adapt to new situations. But if you add a connection cost in addition to selection for performance, then like a switch, you get these modular networks that are beautifully decompose the problem and then turn out to be faster to adapt. And we showed, this is more of the data here. We also showed the exact same thing with hierarchy. So hierarchy is basically the recursive composition of these lower level modules. Similar co-authors, this one led by Hanok. And then we showed, again, if you do not have a connection cost, you don't get these properties. If you do add this cost, boom, you get this kind of hierarchy that shows up in the network and it decomposes the task in a hierarchical way. So I think that's just kind of a nice anecdote of how some things that we think are accidental in nature and not important to put into our algorithms turn out to be important and create important drivers of complexity. All right, so that was just a little prelude. In this talk, what I want to do is I want to describe alternative to conventional neural nets that are loosely inspired by biology that can improve meta learning and continual learning. That's going to involve deep dives into some work that we did on Hebbian plasticity, neuromodulated Hebbian plasticity, and then this algorithm animal that learns to continually learn. So, meta learning, if you have been paying attention the last few years, this is the idea of algorithms that on their own, they learn to learn, so they get better at learning over time. There's two major camps. One of them is that you're going to this is the mammal camp. You're going to meta learn good initial weights for SGD. And then at inference time, you're going to start with those weights and you're still going to run SGD to learn new problems, SGD being stochastic gradient descent. There's a second camp, which I'm really excited about, which is called where you basically just take a recurrent neural network and during training, you're using SGD to train the weights of that network. But at inference time, there is no externally provided learning algorithm. You just run the recurrent neural network. It basically has outputs and it updates its activations and it's storing information it's gathering from the world in its activations. adapting based on that, and then solving a problem better. So it has created its own learning algorithm inside of this recurrent neural network. And we know recurrent neural networks are universal approximators. So in theory, it can create any learning algorithm. And in these two papers here, which I love, they've shown that it does pretty interesting things. So the first two papers in this talk are going to be in this second camp here, and then we're going to return to the first camp. All right, so this idea of learning to reinforcement learn, I just described it a little bit. What you basically do is in an outer loop, you're going to optimize the parameters of this recurrent neural net that you can see pictured here. Those parameters are theta, and you're optimizing them for lifetime performance. So you're going to take this thing, you're going to run it for a while, you're going to see how well it did according to some scoring function, and that's what the outer loop is optimizing the parameters for. And then at inference time, you just run that thing. That's it, and it does good things. So this work is led by Jane Wang at DeepMind. It's a fantastic paper, and it does some really, really interesting, cool things. One of them is that it learns to explore and exploit all on its own. So it's solving these fundamental problems in reinforcement learning. So here's an example of a maze. Here's a bird's eye view. This is what it actually looked like. And this agent is put in this little maze. There's a reward in one of these corners. This is like a 4-arm T maze or something, or I guess 2T T maze. And it basically, you can see it like it explores all 4 corners of the maze. It learns where the reward is, and then it keeps going back to the reward over and over and over again, and learns to solve this problem, which is pretty cool. Somewhat mind-blowingly, it also seemingly is maybe learning its own model of the world and doing model-based planning and thinking of doing like rollouts in its head and then acting on them. And so that's tantalizing and exciting that it might be learning kind of what, complex intelligence does. So the people at OpenAI, before I joined there, did a fantastic job of scaling this up. And they showed that if you just take a giant recurrent neural net and you train it, constantly waking up in a different world that has different properties like friction, mass, et cetera, it learns to conduct experiments, to do system identification, to figure out that what kind of how the world works that it finds itself in, and then it exploits that knowledge to go on and solve the task. How cool is that? It's amazing. So in all of these works, everybody has used a standard recurrent neural network. And what I want to argue today is that even if you believe in this approach and you're excited by it, you still have to make a choice, which is what is that recurrent neural network made of that you're going to do this meta learning in? And I'm going to try to convince you that materials matter. This choice of what we're going to build that network out of matters. And so all of the recurrent neural nets that we've talked about so far in the previous work, they had to learn everything about the world and store that information and condition on that information within the activations of that recurrent neural network. It's kind of like if I gave you a phone number, like 517, da, 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 and you just have to keep saying to yourself 517, da, 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 and you kind of have this loop in your recurrent neural network to try to store that information. It doesn't work very well. It's very stable. It's why our short-term memories, I can't store a really big number in my head. Because storing information in activation loops is just kind of hard and unstable. And so the proposal in this talk is, well, let's do what the human brain does, which is let's take information out of these activation loops and store them in the weights of the network in addition to its activations. And if we give the network the ability to do that, maybe things will get better. So let's take a look. So this is work done by, led by Thomas McConey with Ken Stanley. We did this at Uber AI Labs. So this is a work into differentiable Hebbian learning. So the idea here, I already mentioned that we want to store information in the weights, but we're going to use Hebbian learning. Now, interestingly enough, this Hebbian learning is trained with SGD. So let me tell you what I mean by that. So if you remember from your first ever Hebbian learning class or neuroscience class, the idea behind Hebbian learning is that neurons that fire together wire together. So here is the weight of between two neurons after a time step. That is the old weight, one time step ago, plus a small change if the two neurons both fired, if they both fired positively or negatively. And if that correlation exists, then you will update that weight. You can also decrease it if they're anti-correlated. It's been shown that this has many capabilities. It can do unsupervised learning like PCA. It gets really good at associative recall. And people have played with this for decades in very, very tiny little neural networks, but no one's ever really been able to scale it up and find out what it's capable of at scale. And as we all know from deep learning, scale matters. So Thomas basically did that. He basically figured out how to scale this up. And so the way that this is going to work is that you have this recurrent neural network that's using Hebbian learning. And it basically is going to learn these two components. So here's your typical neural net equation. where the output is just, the dot product of the input, the data and the weight vector. And that's the green thing. We're going to add a plastic part right here. And that is basically going to be a small amount of, an arbitrary amount of Hebbian learning. So you're going to have the Hebbian, kind of the intra-life learned part, in addition to the thing that is provided that is fixed. And then alpha is going to determine the learning rate of that plastic part. So let me say this again. You can almost think about this as if the green part is the instincts provided by evolution. This is the baseline of how this network is going to operate. On top of that, for each weight, you can add a Hebbian component, and alpha is going to determine how much you care. So actually I said alpha was learning rate. Alpha is how much you care about that Hebbian component. So you could choose to zero that out and eliminate the Hebbian component completely. You could choose to make it big and have that weight be mostly dominated by the plastic part versus the fixed part. That's it. That's all you do. So in the inner loop, you're not running SGD, you're just running this network here according to the parameters that it starts with. And in the outer loop, you can differentiate through all of the learning that this network does to the final score function, differentiate back through all of these steps, all of the, this unrolled thing, and train these parameters here. I hope that is clear. If you do that, then at the time you would get near state-of-the-art results on Omniglot. And this was a pretty well-studied data set. So it's kind of cool that a completely different approach can do as well as a lot of the state-of-the-art methods. It also has certain areas where it's not only competitive, but it actually truly shines. So here is kind of an associative recall pattern. You're going to show the network a bunch of patterns. You're going to get about a part of a pattern, like a few notes of a song, and it has to give you the full song back. And what you see here is that a non-plastic recurrent neural network can't solve this problem at all. LSTMs can solve this problem, but they take a huge amount of time to do that. And then look how fast this plastic recurrent neural network solves this problem. It's almost immediate, and its performance at convergence is better. The final thing we wanted to put this network through the paces on was kind of because we're at scale now, is like a relatively high dimensional recall task. So we're going to give it half of a picture and ask it to in-paint kind of the rest of the picture. This is a Hebbian network with over 2 million parameters, which I think is orders of magnitude larger than any other Hebbian network that's been created. And LSTMs just definitely cannot solve this problem. And so, So here you're actually seeing the results, which is, I'm going to play that again. There you can see the quantitative results, and here qualitatively, you can see these kind of images that get in-painted, which are pretty good. Okay, so I said that was the final task. I was actually wrong. There's one more. Here is a maze navigation task. So the idea here is the network wakes up in this maze, and it has to try to get to the green target, and it can only see a local area around itself. And so it has to explore, find out where the reward is, and then return to it over and over again. It's very much like the LRL maze task that we saw earlier. And what you can see is the network clearly gets way better. It starts out random and eventually it gets really, really, really good at both exploring and exploiting. And what we found is that the differentiable Hebbian network really, really improves performance. Which is cool. Another interesting thing is that I mentioned that you have a per parameter learned amount of how much is this weight going to be plastic versus fixed. And that per parameter flexibility really drives performance. So green here is if you only have one parameter for all the weights, which is how much should all the weights be either Hebbian or fixed. That doesn't work very well. But if you can craft and pick different weights are going to have like hard-coded instincts, and different weights going to be very plastic, that's blue here, and you see a huge gap in performance between the two. Okay. The next kind of paper I want to mention is differentiable neuromodulated plasticity, which Thomas called backpropamine. He had fun with that. And so the idea is that even though Hebbian learning is really powerful, as we've just shown, or can be, it's a hard optimization problem still, because everything has to be local, right? Every weight is only updating itself based on really local information. However, a better idea, which is somewhat inspired by what happens in the brain, is what's called neuromodulation, where different parts of the network, like maybe if you have a whole network that says, I'm in a certain situation here, it can turn learning on and off in other parts of the network. So for example, at a high level, imagine like if I'm playing chess and I won, then I might want to turn learning on only in the chess playing part of the network and leave the volleyball playing part of the network alone. And that is what neuromodulation can do. So the way that this works in practice in this paper is here's the same thing I just showed you, the Hebbian learning thing. The notation's a little bit different, but it's the same idea. In neuromodulation, we're now going to basically have an extra neuron here, which is this M part here, and it gets to basically modulate whether or not we're going to include Hebbian updates at this point in time. And so it can basically kind of turn the Hebbian system on and off depending on what's happening in the data that it is detecting as a function of the world that it has found itself in. So if you do that, then basically you end up finding that it works even better than the differentiable Hebbian thing that we showed before. And so there are certain problems like here where it just basically is necessary to solve the task. And here are two different versions of this neuromodulation doing their thing. In this maze navigation task that we showed you, that is, it also, it's basically roughly competitive over there. And so that was exciting. And then on this word prediction task, it performs better than anything that we were able to see before. So that concludes those two chapters of the talk. Now I want to pivot to another problem that is near and dear to my heart. And I think it's a fascinating difference between neuroscience and artificial intelligence, which is this idea of learning to continually learn. It was done with these wonderful collaborators that you can see listed here, led by Sean Ballou and Nick Cheney. So catastrophic forgetting is an Achilles heel of all machine learning systems, which basically is that in any AI that we've created so far, it can learn task A pretty well, and then afterwards it can learn task B. But while it's learning task B, it's cannibalizing all of its all of its information that it learned about task A. In a neural net, it's literally overwriting the weights for task A. It's using them all for task B, which means that it's forgetting how to do and catastrophically forgetting how to do task A. So once you learn task B, you have no ability to do task A anymore. This is not how animals, including humans, work. So I haven't played volleyball, sadly, in like 10 years. But if I went tomorrow and played, I would have to knock the rust off a little bit, but more or less I would pick up where I left off and I would be able to continually learn. Whereas our artificial neural networks do not do that. And so over the years, so in my opinion, we really need to solve this problem. It's kind of a grand challenge of the field. If we want AI that can just continuously learn, like in our life, like be our assistant, for example, and like learn our preferences and what we want, and then not have to reteach it every skill every day, basically. So this problem has been studied for decades, and there've been many, many solutions proposed over the years. And I would put to you that all of them are effectively manual solutions. Here is a giant list of them. There's many, many more. I want to specifically highlight this one. This is because it's an example. So many people believe if the network has sparse activations, so if every single sample tends to light up only a few neurons in my brain, then there's going to be less opportunity for overwriting other neurons because those other neurons basically aren't on. And I do think that's a pretty good idea, but how has this been done historically? They say, all right, we think sparse activations will help, so let's add manually a cost for activations, i.e. a pressure for sparsity. That will produce some amount of sparsity in the network, and then maybe that will help with continual learning. And sure enough, it helps a little bit. And I think this is an example of what I call the manual path to AI, which is, you have to optimize for one thing and hope for another. You really want to learn to continually learn, but instead you don't know how to do that. And so you'll create this auxiliary pressure for sparsity, which you hope will give you the continual learning improvement. And what I would say is we can now switch our attention to the meta learning philosophy, which says, don't optimize for one thing and hope for another, just optimize for what you want. And so the hypothesis is that we're not smart enough to figure out things like how to learn to continually learn. Let's let the system do that for us. And so my proposal is let's just use meta learning to directly learn to continually learn, which allows us to optimize for what we want. And then, so basically what this means is we're going to take a network, we're going to train it on one task, then another task, then another task, then another task. And at the end, we want to test it on all those tasks, see how good it is on all of them, and then have the outer loop optimized for that final performance. How good are you on everything? Or you could just integrate performance across the entire life, things like this. So I promised you we're going to return to the other camp of meta learning, and now we'll do that. We'll go back up to the mammal style camp and show you some work in this vein. So mammal is quite complicated, and I'm going to try to walk you through how it works in the hopes that you can understand exactly what's going on here. So typically in mammal, what happens is you start with an initial weight vector theta. It's random. And then you start doing learning, right? We're learning to learn. So we have to give it the ability to learn for a little while. So you take theta, you copy it, and that's the subscript, is the first iteration of theta. And the superscript is each little time step within this learning opportunity. So you see some data, you take a step of SGD, you see some data, you take some step of SGD, you get to n steps of SGD. Then you evaluate that network. How good are you now that you've had the opportunity to learn in this first task? You can get a loss for this network after n steps. And then here's the mind-bending part. You can differentiate back through all of those steps of learning, including each step of SGD, all the way back to the original weight vector, and get a gradient, which is how should the weights of my initial network have been different? So, how could I change these weights such that the next time I run that whole learning loop, at the end of learning, I will do better on the final scoring function, the final performance, the performance after learning. I will take a step in the original weight vector space. That gives me theta 2. Then I will repeat the process. I'll do that over and over and over again to get a good final weight vector here, theta m. Now, I'm going to introduce some terminology. This is meta training. We're training the network. And then in meta training, you have meta training, that's this, and then meta train testing, that's this thing over here. Now, after those m steps of meta training, we have a weight vector. And now we want to see how good it is. So now we will begin meta testing. So the point of this network is that it learned to learn. So if we want to see if it's good, we have to let it learn something entirely new. So we need a new task here, and we need to give it a few steps of learning to see how fast can you learn. So in meta test training, we will take n steps on some new task, get to the final network. This is using SGD. Then we will evaluate this network in meta test testing to see how good did you do on this task. So I hope I brought you with me on all of that terminology. Now, to go to continual learning, we have to make it just a little bit more complicated. And that is, within each blue box, we want to do sequential learning. We have to have task A, then task B, then et cetera. So here's actually task 1, task 2. We have T tasks we're going to do. For each one of those, we're going to take a few steps in that task, then switch to the next task, switch to the next task. At the end, as I promised, we want to evaluate on how it did on all of those tasks. So it has to learn without forgetting. It has to learn T tasks and still be good on task 1, for example. And that's going to factor into its final performance. Otherwise, everything pulls through. We do the same thing. All right, so we had been working on this for a couple of years and it wasn't working very well. And then I saw a talk by Martha White on her work with her student, Javed. And they had done some really great work with the exact same vision, where they're going to try to learn to continually learn. And I think this validates the vision of meta learning, the solution to really hard problems in machine learning, in particular, in this case, continual learning. And we were inspired by their work and we compared to it. And I want to describe it to you. So they call this OML, or online aware meta learning. And basically what they do is they are going to do everything I just described, except they're going to have a network broken into 2 parts. The first few layers of the network, they call the RLN, the representation learning network. And the second, like the last 2 layers, they're called the prediction learning network. So this basically learns the representations and this classifies based on the representations. And so what they do is that during meta learning, they will learn the blue, and then they will freeze that representation, not allow those weights to change. And then when they want to learn a new task, they'll do a few steps in the red network, calculate its performance, and then they're off to the races. And so this performs really, really, really well. So after sequentially training on 150 classes of Omniglot, it does really well on meta test training, near perfectly, and then it gets pretty good on meta test testing. So on 63%, you get 63% performance on seeing a bunch of tasks. And I'll show you that some more performance curves in a little bit. Another really cool thing about this work is that it on its own learned sparsity. It created sparse activations inside of its network because that's a good idea, but not because they provided an auxiliary loss for sparsity. So let's see that in action. Let's see evidence of that. So this right here, this column is one data input. When you input that data into the network, you can see how the neurons in one of its activation layers light up or not. And what you can see is that on the bottom there, on the bottom there is normal deep learning. And what you can see is it's not very sparse. Many neurons are firing. In OML, only a few neurons are firing for this image. And on this image, only a few different neurons are firing, et cetera, for the third one. And if you look at, if you actually create a penalty for activations, which is to say a reward for sparsity, that's this row here. And you get a lot of, sparsity in the network also. But look at what happens on average across the data set. If you have normal deep learning, you get basically, you're using, some of your neurons aren't even being used, but on average, you're using a lot of neurons. But in the sparsity case, you're kind of like over and, you're turning off huge parts of your network. You're not even using your capacity. This is like an over-eager student that's like, oh, you want me to be sparse? Okay, I'll be really sparse. And so you waste a lot of your capacity because you didn't know exactly how to create the sparsity penalty. But in the OML case, there's basically all of the bandwidth of the network is being used. And so it learned to use it because it wasn't trying to be sparse. It was just trying to learn to continue to learn. And sparsity is a pretty good idea, but it didn't go overboard, basically. So we think OML gets a lot right, but it's still ultimately subject to kind of the tyranny of SGD, which is to say that the red network still wants to forget. It's trying to forget. The fact that you freeze blue prevents that a little bit, but it's still basically forgetting. And so we thought maybe we could do better if we gave it this extra material of neuromodulation. And so the idea, if you recall, is that one part of the network can turn learning on or off in the other part of the network. And that might allow you to, as I said, maybe turn learning on only in the chess playing part of the network and protect the rest of the network. So in my lab at the University of Wyoming, we had studied this for a few years. And in these papers here, we showed that you could perfectly solve catastrophic forgetting in tiny little networks on very simple problems if you added neuromodulation. And so in this work, we wanted to scale that up with the tools of deep learning. And so this work, as I mentioned, was led by Sean, and we initially were struggling to scale it up. And Sean had this insight that maybe that's because you're only affecting the learning in the vanilla version of neuromodulation. That we were using, where you could turn learning on and off. If you're chess playing part of your network and your volleyball plays and volleyball, then maybe you just can't modulate the forward pass as well as the backwards pass. So we call this selective activation. That indirectly produces selective plasticity, and I'll show you that in a second. So the way that this works is that now we have two networks that are kind of in parallel. This network here, the red network. It is going to be a normal forward pass, normal deep neural network. This blue network here also gets to see the data. It gets to decide what it wants to do in terms of learning. And then it basically sends a mask. And via an element-wise multiplication, it can basically gate the outcoming activations of this red network. And that does this. In normal deep learning, you have inference everywhere and learning everywhere. That's why you get catastrophic forgetting. In animal, we're going to allow the neuromodulatory network to gate this forward pass here. That basically turns off, for example, the volleyball muscles during chess, but that also then affects the backwards pass because now the gradients won't flow to the volleyball part of the network when we're playing chess and vice versa. And that basically gets us the best of both worlds. Once we made that switch, everything started working really well and we started getting really nice results. So here is the domain. We're on Omniglot here, and each character type is a class. And so basically what we want is, in an ideal world, there's like 600 tasks. We would want to like allow learning on all of them and differentiate back through all of those. That doesn't work because meta learning is not that stable. And so one of the really nice insights from the OML paper is that we can approximate that ideal, which is by just training on the next task and then testing, gathering your loss on how well you did on that task after learning, as well as how well you did on a random sample of previous tasks that you have learned. And in expectation, that approximates the true gradient that we want in terms of, can you learn a whole bunch of tasks without forgetting any of them? So here's how it looks. In one inner loop, you're going to see a character take an SGD step, see a character take an XGD step. You're going to do that a bunch of times. And then we're going to evaluate your performance on the characters you just saw and a random sample of characters you've previously learned, differentiate back through all of that learning, and then adjust that initial weight vector, take a gradient step, and then repeat the process. At meta testing time, then what we'll do is we'll take a new character that you've never seen before. This is our approximation. This is basically our new task. You will see a bunch of those instances. We will give you the labels, so you get to learn this. And then we're going to evaluate you both on how well you did on those characters, as well as how well you did on held out versions of those. And now all of this is after you saw one new task. So we'll put your performance after one task. And then we'll do the same thing for another task, and then another task, and ultimately as many tasks as we can. And we'll plot your average performance across all those tasks after seeing those n tasks. Okay, so I just want to remind you before I show you any results that deep learning is really, or sorry, continual learning is really hard. In normal deep learning, you have IID sampling over and over and over again of the data. IID sampling of the data. So there's no sequentiality to it. And so there's no issue of learning one thing and then the next thing and forgetting the earlier stuff, because you're constantly seeing a little bit of everything. You also usually have multiple passes to the data. In the results I'm about to show you, you have one pass to the data and everything is sequential. So if you do normal deep learning, these are your results. It totally forgets horribly. So after learning like 100 classes, its average performance on all those tasks is terrible. If you pre-train the network with a lot of compute and then do it, you start off a little better, but you end up catastrophically forgetting similar levels. This is OML, the work by Javed and White, which is really great work. This is pretty good performance. So their paper published out to 150. We went all the way out to 600. And, it's way better than not doing this sort of a thing, but it's still, at the end of 600 tasks, it's still struggling to remember all of those 600 tasks. And then we were able to come up with an architectural improvement over their work that worked better. And then this is animal here in blue. And so you can see a really substantial jump from the original OML work and even the best version that we were able to find of the OML algorithm. And the difference to normal deep learning is just mind-blowing in terms of its ability to learn without forgetting. What's also kind of fun is that you can isolate the effect of sequentiality. I don't know what the right word there is. And the way that you could do that is that you can basically, you can do, the Oracle version is, you cannot just do the IID training of the data. And so instead of presenting the data sequentially, you randomly shuffle the data, and then you see the performance delta between when I saw the data sequentially and when I saw it randomly shuffled. And when I subtract that, when I look at that performance drop, that's kind of the drop due to catastrophic forgetting in some sense. It gets rid of that one pass versus many pass confounder that I was just talking about. So when you do normal deep learning, we're calling that from scratch, then you end up with a 99% performance drop between what you accomplish in the IID case versus the sequential case. And then if you do the pre-training thing, you still get a massive drop. OML reduced that to 47% drop, which is pretty good. Animal reduces it all the way to 8%. So effectively, Animal is eliminating almost all of the catastrophic forgetting that we're seeing in this data set, which I think is quite exciting. Also, just like OML, Animal learns sparsity. So any instance of the data has very few neurons on. Across the data set, it uses all of its capacity. And in fact, in both OML and Animal, there are no dead neurons, which means there's not a single neuron that isn't doing something in some samples of the data set, versus 14% if you try to explicitly encourage an auxiliary loss for sparsity. Now, I want to announce for the first time to the public that there's an update for this work, and that is that Sarah Pellavani at UCL, she was following up on this work, and she basically found something really interesting to us, which is if you take our network here and you delete the blue network, it performs just as well. So that's interesting. That throws out a lot of the story that, that updates a lot of our story in terms of like what the role neuromodulation was playing. We hadn't realized this because when we did this, we were trying to confound for the total number of parameters because that's really important in deep learning. And so when we created this two-stream network, we made each network half as big because We wanted it to be competitive, to be fair to the control, which is the red network, which otherwise would only have had half the parameters. And then we found that, this thing beats OML. What Sarah found is that actually, if you delete the blue network, then it works just as well, which means that the actually key difference was going to a smaller network. So she's going to share more results soon, and we're going to update our paper soon. I wanted to share that with all of you so you have the latest and greatest. I think this is a good example of science. We have a hypothesis for why the results were so good, and it turns out that that hypothesis isn't, the results are way better, but now we don't know exactly why they're so much better. So we're investigating that. But I wanted to flag that for you so you have the full story. So more on that soon. To conclude this part of the talk, OML and Animal can learn 600 sequential tasks and still perform pretty well on average. They learn to produce sparse representations, and like many other things, and likely many other things. It's not just sparsity that's probably they're doing. They're probably doing all sorts of awesome tricks to solve catastrophic forgetting we don't even know yet. And so in future work, we want to try this on more and harder domains, and we want to try other flavors of meta learning, such as recurrent neural networks, like the stuff in the first two papers that I talked about in the talk. Okay, so now in the time that remains, I want to zoom way out to the grandest ambitions of our field. Going all the way back to the founder, Alan Turing, we've been interested in human-level AI, or some people call artificial general intelligence. I think we all agree that we have a long way to go, although we've been making a lot of progress. And so the question I think is interesting is, how will we get all the way there? Not how will we do the next thing that we'll put at the next conference, but like, what's the real path that we're going to use to get all the way there? I think if you look around, what you'll see is that at every conference I go to, almost all of the papers are what I call the manual path to AI, which you've seen some of it already in this talk. The basic idea is that we're in phase one, we're going to identify all of the building blocks in artificial intelligence. And if you look at any conference like NeurIPS or ICML, what you'll see is like a paper that's like, oh, here's a new building block I think we're going to ultimately need in our learning machine, or here's an improved version of an existing building block. And here's just a list of some of the things that people work on and publish papers on. But this, seeing this list raises this question, like, how many more of these building blocks are out there? Are there hundreds? Are there thousands? Can we find them all manually, as we've been doing? But even if we could find them all, that implies some other phase, which is eventually we're going to integrate them all together into some complex thinking machine. And I just think we should be clear-eyed about the fact that this is a Herculean task. Think about debugging this thing and putting it together. Like, if something doesn't work in this giant machine, like, how are we going to figure that out? It's going to be a significant undertaking, and that's hard. I think that if you look to machine learning, though, there is this really clear trend, which is that hand-designed pipelines are ultimately outperformed by learned solutions as you have more compute and data. We've seen that with features. We've seen that with architectures, where increasingly the best architectures are learned, not hand designed. We're seeing that increasingly with hyperparameters and data augmentation pipelines. And then in all the learning to reinforcement learning stuff I've talked about, you're starting to see that with the RL algorithms themselves, which are being improved upon. And so I think this suggests an alternate path. And that's what I call AI generating algorithms. The idea here is to learn as much as possible of the entire solution to machine learning, to bootstrap from simple to AGI via a system that starts out really unintelligent, but gets smarter and smarter all the time, and ultimately produces a sample efficient learner. Now, we've seen that this can work, because on Earth, the very unintelligent algorithm of Darwinian evolution produced the human mind, and we are the most sample efficient, impressive learner in the known universe. So if we want to make progress on this, I think we have to simultaneously push on three pillars. We have to meta learn the architectures, because transformers aren't going to be the last architecture that we want. We have to meta learn the learning algorithms themselves, like in learning to reinforcement learn. And we have to automatically generate the learning challenges so that the system can bootstrap itself up, pick its next challenge, and go learn it. Handcrafting each of these is slow and limited by our intelligence at time. So I think it's better to learn all of them automatically and let machine learning, compute, and data do the heavy lifting. So today we focused on pillar 2. If you're interested, my work and other groups have been doing work on architecture search, like Esteban Real and Clune have done fantastic work. We've done this work here in purple. You could check that out. I've also done a tremendous amount of work with my colleagues on pillar 3 to try to automatically generate effective learning environments. And I gave an entire keynote actually on this exact subject. And here is a link, or you can find the link on my website at Coral, where I focus on this. So to overall conclude the talk, I first described Hebbian, differentiable Hebbian plasticity, which is basically taking the old Hebbian thing, but now figuring out how to train it with backprop at massive scale. We also introduced that you can add neuromodulation to that and kind of add that as an extra material in the soup that machine learning can play with. I also described the animal algorithm, which I think is a nice, along with OML, is a nice indication that we should just learn the solutions to the hardest problems in machine learning instead of trying to manually design them or manually create auxiliary pressures. Let's just directly train for what we want. And then finally, I've introduced this new paradigm called AI generating algorithms, which I really think is potentially the fastest path to AI, where we're just going to really go all in and commit to learning the solution. And any other work is kind of basically that might be the best place to put our efforts, and it might be the most promising direction. In all of these works, I hope I've convinced you that material matters. Hebbian plasticity helps versus normal recurrent networks. Neuromodulation can help. And I think that raises the question of what other materials should we be building with? What secrets do we need to take off the shelf from biology, from nature, inject into our AI generating algorithms and meta learning algorithms to make them faster and better? And maybe we could search for those things as well and automate that. So with that, I want to say thanks to all of my fantastic collaborators, especially the lead authors on the works, the funding agencies, and some of the organizations where I did the work. And here is where I am standing right now at lovely University of British Columbia. And so if you're interested in working on these things or collaborating with me, then you can come visit here and hang out by the ocean and work on these fascinating problems. Thank you again to the organizers for the invitation. I'm happy to take any questions that you have.